In this video, we'll discuss how to find the pH for a weak acidic solution. Recall this general form for a weak acid that is represented with HA. It is a proton donor to the water molecule and makes hydronium, H3O+. This is what we want to find in order to calculate the pH of a weak acidic solution, because we can calculate pH by taking the negative log of the hydronium ion concentration. Also recall that this is a reversible reaction and therefore has an equilibrium constant, Ka, also known as the acid dissociation constant, and can be calculated using this equilibrium expression from your reference packet. The next few slides take us through the steps that we will work through in order to find the pH of a weak acidic solution. Of course, we always want to start with a balanced chemical equation, and it could be more than one that produces hydronium ion in solution. So we'll want to take a look at all the reactions and then consider which reaction is going to be the most significant source of hydronium ion in order to calculate out the pH. For example, if we have a mixture of weak acids, we're going to go with the stronger acid as the source of hydronium. Remember, with a stronger acid, you're going to get a higher Ka value. If you have a polyprotic acid, an acid that can donate more than one proton, usually we're just going to look at the first step, the first proton being donated as the most significant source of hydronium ion. Once we made a decision about our reaction and where our hydronium ion is coming from, then we'll write our equilibrium expression. And then we go into the steps for an ice chart. We'll look at initial concentrations. We'll define changes in concentration in terms of X. We'll substitute into our equilibrium expression and try to solve for X. We will see if we can solve for X the easy way by just talking about the initial concentration as being essentially unchanged instead of the initial concentration minus X. We can double check when we're all done solving for X with the 5% rule to make sure that was a valid way to solve the problem. Then we can calculate our hydronium ion concentration and our pH. Remember, these Ka values, these equilibrium constants, are going to be very small, so usually it is okay to omit the minus X when we are solving for X and then check it with the 5% rule. Let's say we were going to do a problem with hydrocyanic acid, a weak acid, represented here in the first equation. You can see that it does produce hydronium ion, okay? And this hydrocyanic acid is also in water, and if you remember, water auto-ionizes or self-ionizes to also produce hydronium ion. The Ka for the hydrocyanic acid is 10 to the negative 10th, and the Kw for water is 10 to the negative 14th. So this means that the hydrocyanic acid is going to be a more significant source of hydronium ion. And so when we do a problem with any weak acid, we will always look at it as being the more significant source of hydronium ion compared to water. So we're going to ignore this, and then we'll go through our problem and we'll work with the Ka for the weak acid. So let's take a look at a problem with hydrofluoric acid, HF. Here is the equilibrium system and the Ka value. We want to find the pH of a 0.5 molar aqueous solution of our hydrofluoric acid. So we're going to go into an ice chart. The initial concentration of the hydrofluoric acid is given as 0.50 molar. We're going to ignore the water since it is a liquid. We will never fill in anything for water in our ice chart. And we're going to assume our hydronium and fluoride ion concentrations initially are 0. So as our reaction shifts right and we make hydronium and fluoride ion, we are going to see a decrease in our concentration of hydrofluoric acid and an increase in our hydronium and fluoride ion concentrations. At equilibrium, the concentration of the hydrofluoric acid is going to be 0.50 minus X, X for hydronium and X for fluoride. Here is our equilibrium expression, products over reactants, not including the water, and I can substitute in my equilibrium concentrations. For my equilibrium concentration of the hydrofluoric acid, I'm going to see if I can do the problem with just the 0.5 as opposed to the 0.5 minus X. And that simplifies to X squared divided by 0.5 is equal to the Ka. My Ka is 7.2 times 10 to the negative fourth. I'm going to substitute that in, set it equal to X squared divided by 0.5, and then solve for X. X is equal to 0.019, rounded to two significant figures. I can double check with the 5% rule to make sure it was okay to do the math the easy way. And if you recall, we're going to take the value for X, 0.019, and we divide it by that initial concentration of 0.5, multiply by 100 to make it a percent. And if it's less than 5%, which it is 3.8%, it was okay to do the math the easy way. The change to the concentration of the HF is going to be very, very small. So we're almost done. We want the pH of the solution, and pH is the negative log of the hydronium ion concentration. So once we have X, we have the hydronium ion concentration. We're going to take the negative log of 0.019, and that will give us the pH of our hydrofluoric acid solution. That gives me a pH of 1.72. I did 2 decimal places on my pH since I had 2 sig figs in my hydronium ion concentration. This does make sense as a pH for an acid, 1.72, and that's how we do pH for weak acids. Another thing we like to be able to talk about with weak acids is the percent dissociation or ionization. So to what percent do we actually get our products, specifically our hydronium ion? So our percent dissociation or ionization is the concentration of that hydronium ion at equilibrium, so X, in relation to the initial concentration of the acid times 100 to make it a percent. We will work on calculating that in a moment. But first, let's talk about the relationship between acid concentration, hydronium ion concentration, and percent dissociation for a weak acid. As the concentration of a weak acid is increased, the amount of hydronium ion in solution increases as well. But what is a little counterintuitive is that as we dilute a weak acid, as it becomes less concentrated, the percent dissociation actually increases. And here's why. As we're diluting our acid or adding more water, our reaction is going to shift to the right and increase the amount of ions in solution of hydronium and the conjugate base. So then we would say we have an increased percent dissociation or ionization when we have more ions in solution. Let's start by calculating the pH of a 4 molar aqueous solution of formic acid. I'm just using the general form of the equation here. The Ka for formic acid is 1.8 times 10 to the negative fourth. Pause the video here and see if you can find the pH of this solution using an ice chart. In my ice chart, I start with an initial concentration for my acid, HA, as 4, and then minus X, plus X and plus X on the products. And then I substitute into my equilibrium expression. X squared over 4 is equal to 1.8 times 10 to the negative fourth. Once I solve for X, I get 0.027 rounded to two significant figures. Once I know X, this is my hydronium ion concentration. And for pH, I take the negative log of the hydronium ion concentration to get a pH of 1.57, which makes sense as a pH for an acid. And I'm done with my problem. Now let's talk about the percent ionization or dissociation of that same 4 molar formic acid solution. We're going to take our hydronium ion concentration at equilibrium. This is also known as X, and we're going to divide it by that initial concentration, multiply by 100 to make it a percent. Our value for X, or our hydronium ion concentration that we just calculated, was 0.027. We'll divide that by the 4 molar, the initial concentration, times 100 to make it a percent. And our percent ionization or dissociation for our formic acid solution is 0.68%. And if you're thinking, isn't this the same thing we do to double check with the 5% rule on an ice chart? You are absolutely correct. So we are actually calculating two things at the same time, the percent ionization or dissociation, and we were double checking our math shortcut with the 5% rule. By the way, you can also solve problems that give you a percent ionization or dissociation and ask you to work back to a Ka value by doing this process basically in reverse. If you're given a percent ionization or dissociation and an initial concentration, you can solve for the hydronium ion concentration and then work it back through an ice chart to find the Ka value. Finally, let's do some comparisons of two different formic acid solution concentrations. We just calculated the percent ionization and the pH for a 4 molar formic acid solution. Let's say we had an 8 molar formic acid solution. So first question, what about the Ka value? As long as the temperature doesn't change, the equilibrium constant or acid dissociation constant shouldn't change. So if we have two different concentrations of the same acid at the same temperature, those Ka values should be the same. What about percent ionization for these two different concentrations of the same acid? A couple slides ago, we said that the percent ionization or dissociation for a weak acid would increase as the acid becomes more dilute. So for an 8 molar that is more concentrated, we should see lower percent ionization compared to the percent ionization for a 4 molar formic acid solution. And what about pH? 8 molar versus 4 molar. When you have a more concentrated acidic solution, you should get more hydronium ion in your solution. And that actually lowers the pH. So the more hydronium ion you have in your solution, the lower your pH will be, or the more acidic your solution is. Here's all the math confirming what we just talked about in the last couple of slides. In my ice chart, X is equal to 0.038. When I put in 8 molar, I get a pH of 1.42. For the 4 molar solution, we got a pH of 1.57. So this is indeed lower. And the percent ionization or dissociation is 0.47% for this 8 molar solution compared to 0.68% ionization for the 4 molar solution. So this is indeed a lower percent ionization with a higher concentration.